Hello, my name is Dr. Abrahamian, and in this channel I go over problem solving strategies primarily in math competitions. In this video we're going to go over problem A1 from 2025 Putnam math competition. Let m0 and n0 be distinct positive integers. For every positive integer k, define mk and nk to be the relatively prime positive integers such that the ratio of mk and nk is the same as 2mk minus 1 plus 1 divided by 2nk minus 1 plus 1. We want to prove that 2mk plus 1 and 2nk plus 1 are relatively prime for all but finitely many positive integers k. Okay, so I started looking at this in two different ways. Neither of them really worked, but when I combined these two ideas, I ended up getting a solution. So first, let's take dk to be the GCD of these two things, 2mk plus 1 and 2nk plus 1. So I want to show that this dk is almost always 1. If dk is more than 1, what does that tell you? It tells you that when I look at 2mk plus 1 divided by 2nk plus 1, I would get mk plus 1 divided by nk plus 1. So this guy would have to be 2mk plus 1 divided by dk, which is less than mk because dk is at least 3. If dk is more than 1, it cannot be 2 because it divides an odd number. So that tells me that mk plus 1 would have to be less than mk. But this is really not causing any issues because maybe mk plus 1 is less than mk, and then mk plus 2 becomes more than mk plus 1, and it increases, and then it decreases again back down. So it didn't really cause any issues. So then I thought maybe I can take a look at what happens if something divides 2mk plus 1 to nk plus 1 and then see what happens. Well, if 2mk plus 1 and 2nk plus 1 are congruent to each other mod some number, let's say mod a prime, that tells me that mk and nk would also have to be the same mod this prime p. Now if I multiply these by the GCD of 2mk minus 1 plus 1 and 2nk minus 1 plus 1, I get that these two are also the same mod p, which means mk minus 1 and nk minus 1 are also the same mod p. And then I can kind of go down, and then I can say that, well, this p would have to divide m0 minus n0. But this number is not 0, so it has only finitely many divisors. So it felt like this should give me a contradiction. So because of that, I decided to look at the difference of mk and nk and see what happens. Well, we had dk is the GCD of 2mk plus 1 and 2nk plus 1. So what does that mean? It means 2mk plus 1 is equal to m sub k plus 1 dk, and 2nk plus 1 is equal to n sub k plus 1 times dk. Now if I take the difference of these two, which I talked about the motivation of that, I would get this. I would get mk plus 1 minus nk plus 1 times dk. Now notice that this dk is an odd number. So what do I get here? If I write down this one, so 2mk minus 1 minus nk minus 1, that would be mk minus nk times dk minus 1. If I repeat that, I would get 2m0 minus n0 is equal to m1 minus n1 times d0. If I multiply all of these, I notice that these are going to cancel. So basically, I get a telescoping product, and this gives me a power of 2. It doesn't really matter what power of 2 it is, but it is 2 to the power of k plus 1 times m0 minus n0 is equal to, on the other side, I would get m sub k plus 1 minus n sub k plus 1 times the product of d0 all the way to dk. So, well, this quantity is odd, and this quantity is a power of 2. So this means that odd number d0 all the way to dk would have to divide m0 minus n0, which means this quantity d0 all the way to dk is always between 1 and m0 minus n0, which is a fixed number. And that's exactly what we wanted to prove. And that brings me to the end of this video. I will see you in the next video.